first things first, we will talk a lot about source routing, which is, again, that ancient technology that has existed as long as the internet, or probably longer, where the whole idea is that you will encode the path of the packet in the packet's header, and then let the routers or switches along the way just read that header and forward accordingly. There's a lot of benefits to that approach, and we'll talk about them. Segment routing, on the other hand, is just the most current instantiation of source routing. There's many other ways to do source routing. I'll mention some of them in the next slide. But segment routing is basically about announcing these segments into the IGP and then making them available to everybody so that an ingress router can then construct a packet header that has a sequence of these segments. And everybody just follows that sequence in the forwarding of the packet. And then Spring gets used as well. Spring is simply the IETF, the name of the IETF working group who is in charge of making sense of all this. So in source routing, the key idea is basically to, like I said, prescribe the path of the packet in the header itself. Don't make routers make independent decisions. Just tell every router how this packet is going to be forwarded. And then every router just follows that instruction. This is very useful, at least in two ways. One is that loops are by definition sort of avoided. Why is that? Because the source simply says where the packet is going. There is no middle router that makes an independent decision about how to forward the packet. So there's no such thing as a routing loop unless you have a bug at the source, and the source can make the packet chase its tail, but that's a bug. The other nice side effect of source routing is that it reduces the forwarding state in the network. There is no need for every router in the network to make up its own mind as a result of routing protocols and other signaling how to forward packets. Instead, all the information it needs to know is already in the packet. So there's a bunch of historical examples about on source routing. A lot of them tend to be about closed niche type of interconnects used in high-performance computing, and some layer 2 forwarding technologies, token ring being kind of the most known about it, most known. All of them use source routing at its sort of core. IP itself has source routing mechanisms. In IPv4, there's these extension headers that got defined that allow a source of the packet to put a sequence of IP addresses over which that packet needs to be forwarded. And in IPv6, there's a separate extension header that is defined. Now, unfortunately, IP source routing never really caught on. And that is because there are all these security holes that were discovered quickly in IPv4, and sadly, in IPv6 as well. IPv6 did not get this right. In fact, by the power of a full-blown standards track RFC, source routing is forbidden in IPv6 packets. Now, a word about tunneling. And more specifically, what happens when you marry tunneling with source routing? Now, the reason source routing is considered insecure is because if somebody is giving me a packet with a bunch of source routing information in it, it's fairly easy for that somebody to make me steer that packet in ways that are malicious. Now, if I was sitting here as a service provider on the boundary and somebody gave me a packet, but I was tunneling that packet in a tunneled encapsulation that I control, that's kind of a different story from a security perspective. The customer packet can have whatever it wants, but I'm tunneling it in this packet, and then I'm just forwarding the tunneled packet within my network, and then on the other end, I'm kind of dumping it out. So fundamentally, the combination of tunneling and source routing is considered more secure. So it's a better thing. This is incidentally exactly what segment routing does. Segment routing is truly the reason why we are revisiting this conversation about source routing in general, because segment routing is the new sort of shiny toy that uses source routing technologies, and is very attractive for a variety of reasons. So fundamentally, segment routing does just that. You know, it tunnels the packets from the source, and then it also encapsulates in the header of the packet a prescribed path by way of segments. And we'll kind of go through a little more details on that. So this is my section that I'll try to go through quickly, where we cover the basic fundamental concepts of segment routing. Hopefully, this is not completely new for everybody, but it's not boring either. So let's see if this can make sense. So segment routing brings in two fundamental building blocks, two fundamental concepts. One is that we're going to assign a segment, or in MPLS terms, a label, for all of our immediate neighbors. So not only we're going to assign that, but we're also going to propagate or flood those segments as part of the IGP. We're going to make each link has a property of a label as well. So that's easy. And once that's done, then every Ingress router has the capability of simply constructing a packet with a header that simply describes the sequence of links that I want to traverse to get to the destination. So in this case, R1 wants to go through R7, and he's going to use that sequence of labels. Now, in my talk here, I'll talk about, there's two data planes for Spring. One is MPLS, the other one is IPv6. I will kind of assume MPLS here, just to keep things simple and consistent. Whatever I say here for MPLS, there's an equivalent thing for it in IPv6 as well. So adjacency label is the first type, or adjacency segment is the first basic segment that segment routing defines. And it is kind of the thing that I described in the previous slide. It's a label that points to an adjacent neighbor. So everybody here will have to define or make up a label that represents their adjacent neighbors and needs to sort of inject those adjacencies or adjacent SIDs into the IGP so that everybody can hear them. And that way, an Ingress router can, R1, let's say, wants to send a packet to R5 via this path. That packet will have this content of the label stack. Does that make sense? Pretty simple. Now, so far, this is not really earth-shattering technology. This is not the big idea of segment routing. I'll make a few observations. One is, by doing just this, we will reduce the amount of state that exists on the routers, and we're going to move that state into the packet headers instead. Okay? Remember, state doesn't disappear. State is like, it's got to be some sort of law of physics. State doesn't disappear, it just moves from here to there. Now, the absence of state is a good thing if you are resource constrained on your devices. But the price you pay is that if you wanted information that state gave you, such as per LSP statistics, for example, you kind of lose that. Okay. It also is a pretty trivial method of forwarding, what I described so far. it requires a pretty deep label stack to be pushed on each packet in order for you to describe all these paths in the network, okay? And pushing deep label stacks typically needs to be done with pretty beefy hardware, or you need to do it at the host in software, okay? So it doesn't lend itself to kind of cheapening the network. Then again, there's the notion of a loose hop as well, just like in traditional MPLS. If you didn't really care to describe the path in that level of detail, you don't have to put all that level of detail in the packet. And then you can just use shortest path forwarding for pieces that are missing in the header. Now, the more interesting concept that Spring brings, or segment routing brings, is this notion of a node SID, or a node label. And this notion, I will talk about it in 2 slides. The first slide is how this notion got initially conceived. And the second slide will be how this notion actually got implemented in practice, because there are a couple problems with the initial conception of this notion. So node segment, the idea is that each node in a segment routing network will announce a segment that everybody can use to reach that node, regardless of the topology. In other words, R7 is going to say, I shall be known by 107 throughout this network. And then everybody, R1, R4, whatever, all they need to do is put a packet with 107 on top and nothing else, and everybody should be able to forward that packet to router 7. So this is pretty cool because we don't have to do deep label stacks. And if we don't care about traffic engineering or being specific about the path, it provides us a very elegant and cheap way to do tunneling of packets through the network, just following the best path. And then you can imagine a combination of using those 2 things, node SID and adjacency SID. If I wanted to be specific about some of the path, but not other parts of the path, you can do combinations of those things. Now, the problem with this initial conception of a global label is that it kind of doesn't work well with MPLS. Well, it doesn't work at all with MPLS. Because in MPLS, one of the fundamental tenets is that each router gets to assign his own labels and announce them to other people. Now, what happened here is R7 just told everybody else, hey, you're going to use 107 here. I don't care if you may have assigned 107 to some other purpose. You're going to change that and in order to use 107 for me. Now, that's a problem, 2 levels at least. One is that it's a problem with interoperability between segment routing and other labeled protocols, like RSVP and LDP. And the other reason it's a problem is it's also a problem of interoperability between vendors. Because if R7 was a Cisco and it was capable of supporting label range that included 107, the next hop router might be Juniper or Alcatel or whatever, and that router may have pre-allocated that label range to some other purpose. So you can't assume these things. That's why MPLS requires local label allocation. Now, turns out that this problem is easy to fix, and it got fixed. But so it got fixed with this notion of SRGB, or source routing, segment routing global block. So what we're going to do instead here is we're going to assign this thing called index to each router, and the index is going to be globally significant. Just like the labels, but not a label, actually, just an abstract index. And then each router is going to announce to the network a label range of labels that he is happy with, that he can work with. So, for example, this is an example of R6 kind of being the black sheep here in this network and having a different label range than anybody else. Let's say R6 has allocated that normal 100 to 199 range to to RSVP or to LDP or whatever, and now wants to allocate a completely different range out of the blue, or out of the yellow here, that is 200 to 299. Now, this combination of using a global index and a locally managed label range is something that allows everybody to be happy. Router 7 is still going to be known by index 7, but the actual label that people are going to use to reach index 7 may change from hop to hop. And in this example, I have an example of how R4 is going to calculate a label of 107 in order to reach router 7, but R5 is going to calculate a label of 207 because that's within its label range. Okay? I'm not going to belabor too much on this because we only have half an hour. So the observation I'd like to share here are that this allows you to have your cake and eat it too. So have node segments, this simple single label way of targeting packets to remote nodes regardless of the topology between here and there. It ensures interoperability both between vendors and between various label protocols and segment routing. So anyway, those are pretty much the main advantages of this. You will encounter all kinds of other terms in segment routing, and they'll probably be talked about in the next presentation as well. There's different kinds of segments or SIDs. There's binding TLVs that connect segments to traditional tunnels, and all kinds of other stuff. Pretty much irrelevant to this talk. I just kind of mentioned it here that there's more to this. All right, so let's talk about what are these nuggets of goodness that segment routing has brought in that can be actually taken and decoupled from the technology and used all over the place. Because let's face it, you can build a greenfield segment routing network. That's one way to achieve the goodness of segment routing. The other way is if you have a large traditional MPLS network to take some of these ideas and apply them there. So this is what I'd like to share next with you. The two nuggets that I want to talk about are predictable label values and the notion of this node SID. And those things are good for a variety of reasons. Predictable label values are really great for troubleshooting, especially if you start introducing controllers into your network. They're good for troubleshooting because instead of figuring out which the label needs to be on this link, you just know what the label is. So you've saved one step of troubleshooting. And if the label doesn't change, you've saved a bunch of other steps of troubleshooting. If you're incorporating a controller, it's also really great to not have that controller learn labels from the network, but instead just know what those labels are going to be. And then the notion of a node SID. Now, keep in mind, node SID is nothing more than a destination IP address. If we were doing just straight IP forwarding, what do I do on destination IP address? I say, I want to send a packet from me to that guy via 10 next hops, but I don't even know about them. Node SID basically does exactly the same thing in segment routing, except it incorporates tunneling of that packet through your network. So it kind of combines the goodness of segment routing, or well, in this case, combines the goodness of just normal destination-based forwarding with tunneling without much state. So those two things are useful to be done not just in segment routing, but elsewhere as well. So if you read through the numerous segment routing Spring-related drafts, you will probably find this one which talks about how you can use segment routing for OEM purposes or for injecting probe packets through your network and exercising all of your links in the network. Source routing is really cool for that because you can just tell, I want to exercise not just the best path, I want to exercise all these paths that exist in my network. And I'm going to do that by just describing the path of the packet in the packet. So that was one of the first use cases that came out for Spring. So an example would be, if I constructed this packet. This packet basically tells R1, I want to traverse this network clockwise, and I'm going to use a label here, 403. And this label actually, or this segment, identifies the lag link or the aggregated link. And then there's these other labels or the other segments that got assigned that actually identify the individual participants in this lag. So then you can construct a different probe that says, hey, this one, I want to do the same thing, except I want to deterministically exercise the upper link of that lag. So that's kind of neat, because when you're doing OEM, you not always want to depend on the hashing of a particular vendor on a lag and how that packet is going to end up hashed. An OEM probe is really useful to be kind of deterministically routed. So you can do that with segment routing. And then conversely, if you don't particularly care about which way you go, and you want to focus on exercising that lag, you can use this node SID of 404, which basically says, I want that packet to get to router 4 somehow, shortest path, and then I want to exercise that upper link. So you can create these probes that are really sort of detailed. Now, it turns out that you can do those things by other means as well. Google actually a few nanogs ago shared a presentation of their system for exhaustive path monitoring. I forget how they call it in this presentation, but it had something to do with black box monitoring. So you can watch the video actually of that stuff. But the highlights are basically, in their case, they created a full RSVP mesh between all of their paths, between all of their routers. And that RSVP mesh was specifically for OEM traffic, like completely outside of the normal data plane RSVP mesh. And then they just started injecting packets into each tunnel. And that's how they, achieved this full link coverage. Problem with that approach is that they just doubled the amount of RSVP state that their routers need to maintain, because they have an RSVP mesh for the normal traffic, and they also now added another RSVP mesh, which is just kind of going in the opposite direction of where they want to go as far as scaling and scaling capabilities. Other customers have taken that idea and actually implemented the same thing with static LSPs, which takes care of that problem of creating that extra RSVP state in the network. So what they've done is they've done constructs like this in their routers, which basically, the key here is knowing the predictable labels. So they assign these predictable label values and allow a path monitoring server to actually inject packets that with appropriate label stacks that follow these values. So basically, my point is that they took the same idea of predictable label values. They used static LSPs, and they kind of achieved the same goal. Second use case is one of more interesting and somewhat controversial nature. Some people want to run MPLS in their data centers. Now, I know that's it's kind of a four-letter word for a lot of people, but VXLAN is the thing and all that, right? Turns out that MPLS has a lot of nice properties. One of them being that it's cheap to implement. It's 20 bits versus however many bits the VXLAN header is. The other one is that it actually provides uniform encapsulation for however many levels you want. That's kind of a neat thing. So in this case, and there's a reference you can read from some guys from Yandex. In this case, they want to have a three deep label stack. The topmost label identifies the destination top of rack switch that you want to go to. And then the second label, the green one, defines the port out of that switch, or otherwise defines the server that you want to go to. And then the third label identifies the virtual machine within the hypervisor. So they take MPLS all the way to the hypervisor. Now, for our purposes here, how you manage these two labels, the bottom two labels, is kind of out of scope. This is managed by a controller assigned by static means. Controller pretty much says VM1 and server 1 shall be label 1. It's like some sort of database that a controller comes up with. The more interesting part is how do you manage the top label, the one that gets you to the egress router, to the egress Tor, and how do you, especially if you want to incorporate a controller in this thing, which you do, how do you tell the controller about all these labels? And how do you make them consistent? So one way to do it is to just create an RSVP mesh in the data center. People don't like that idea because data center devices usually don't scale all that great for RSVP. It's just not really good design approach, probably. You could actually upgrade to SR-capable gear as well and do this with node SIDs. That's what node SIDs are for. Or you can get creative and do something like this. So you can enable any flavor of label distribution protocol in your data center. In this case, this example is with BGP labeled unicast. But you could do LDP as well, just as easily. So BGP labeled unicast does a really good job of advertising loopback addresses and assigning labels to them, like in this case. Now, the problem is that it assigns label values that it wants to, its own by its own decision. Like in this case, sorry, whoa. In this case, it assigned, let's say, 299840. Now, how does a controller know about that label? At a minimum, the controller will need to be a BGP listener and read that label from every device. If that label changes, the controller needs to react to that change. It's kind of a messy, very tight control loop that you would rather avoid. So what's the goal to avoid it? The goal is to come up with a way to have a very statically assigned fixed label, node SID, think node SID, that everybody uses in order to get packets from anywhere to Tor3. Basically, Tor3 is known by label, what is this, 1,000,003 to a whole network. Yet, the actual labels that are flying around in the network are nothing like 1,000,003. They're 299,840. Okay? So the way you do that is by having some clever LSP stitching, where this construct basically says, if you should receive a packet with 1,000,003 on top, so that's what the controller would construct. The next hop for that packet is 3333, which is Tor3. And I want you to stitch that packet to whatever labeled path is available to you. In this case, it's BGP labeled unicast, could have been LDP, could even have been RSVP. So what you have achieved with this whole juggling here is the ability to reference every egress Tor with a fixed known label value. And you don't have to configure any sort of static labels in the network either. You can take advantage of still a dynamic label distribution protocol in the network, as well as you didn't create a full n-squared RSVP mesh either. So that's a good thing. All right, last example that I want to talk about is Egress peer engineering. How many have heard of EPE as a buzzword? A fair amount. So EPE started to be talked about widely, again, as part of all the work around Spring and segment routing. Now, EPE is not a new idea at all for operator community. This is as far back as I can tell that it was discussed. It was probably discussed even earlier than that. The whole idea is that people want to be able to steer. They want to take the peering router out of the business of best path selection. They want to steer traffic that is egressing their network, that's leaving their network, based on other criteria, business logic, link utilization, whatever you name it, not what BGP is telling them. Okay, so that's kind of the idea of EPE is to override the BGP best path decision at the peering router. And the way you would do that is by creating this overlay. And this is the way that's proposed to do in Spring. So you create this overlay, and then you have a controller, and the controller gets adjacency, or in this case, they're called peering SIDs that identify each of the peers. And it also gets a node SID for every peering router. And then it also gets a feed of all the actual routes that are being learned. So at this point, the controller is in a position to actually making a best path selection for every route. And that selection can be augmented based on business rules that the company has. And then that selection can be fed into the ingress of traffic, be it the host or that ingress router. So I will kind of go quicker through this slide. I don't think we'll have time to go through all the numbers, but my point is that the whole idea has been implemented outside of segment routing by using simply BGP labeled unicast and BGP-LS to distribute the same information to the controller. And in this case, you would use, actually, my next slide is what I meant to talk about. So the same information can be disseminated using either IGP or BGP-LU or BGP-LS. There's a bunch of protocol choices for that. The bottom line is that the controller can come up with exactly the same EPE tunneling policy, and it can impose it on the ingress of the traffic. And then you can achieve the same steering that you would with segment routing. In this case, for example, the example is if you look at that table in the middle, my steering policy says, hey, I want to split routing for my segment. Let's say I have a prefix of 8.0/16. Sorry, 8/8. And let's say I want to split the traffic going to that A/8. It's a big prefix. I'm going to split it going two ways. Well, I can do that by creating this EPE policy that says for the upper half of that /8, for the upper /16, send it via peering router 1, and for the second half of that /8, send it through the other peering router. So you have basically overridden the BGP best path decision, and you've steered your traffic based on your administrative policies. There's a bunch of improvements in BGP-LU that make this work better, particularly in terms of protection. Because once you start tunneling, once you prohibit routers from making best path selection, you need to take care of what happens if links fail on those routers. So there's a bunch of improvements around how to handle failure modes. You can kind of check them out in the slides. And that's basically it. This talk was more about, most talks on segment routing tell you how to do existing things with segment routing. This one is more the other way around. It tells you how to take ideas from segment routing and apply them to existing networks. So hopefully some of these made sense. If you guys want to stop by the Juniper table after that, we'll have a chat about it. Thank you.